Okay, so here let's go to the second part of the problem. We have a series circuit that for 3 resistors that looks as follows. So 3 resistors. Again, I will put an ammeter in there. And again, that was a sorry excuse for an ammeter drawing. There we go. And now it says that we have a voltage of 100 volts and we have 3 resistors of 50 ohms, of 30 ohms, and of 20 ohms. There's also a reason why I chose these numbers, why I chose this one to be 100 volts and why I chose these 3 resistors to add up to 100 ohms. And you will see that as we go to the simulation. Okay, first of all I'm gonna unhook the voltmeter and actually take it out of the way, and I will see if I can remove that light bulb. Oh, notice? As soon as I removed one, nothing works anymore. As soon as I reconnect it, there we go. So in a series circuit, if you remove one of the components, or if it breaks down one of the components, then the others are not working. And that, of course, what the book is telling us as well. Okay, so I'm going to take this one out here, and I'm going to take this one out. I didn't mean to connect that. Okay, keeps connecting these junctions here. It keeps doing that. I cannot move it away. Just let me move it away. Oh man, there we go. Alright, so I put a resistor in here. Oh yeah, the first one is actually 50 ohms. And the next one is gonna be 30. Show the value. And the third one is gonna be 20. Show the value. And then I put this one in here, and then it's already working, except I have to change the voltage because it says 100 volts. Alright. And we already see the result here, one of the results. The current is 1 amp. And that also means that the power being consumed is 100 watts. 1 amp times 100 volts, which is 100 watts, and just show the value. Okay. Again, for a series circuit, it says the voltage drop across each device is proportional to its resistance. Ohm's law applies separate to each device. And that's why it shows them as 50, 30, and 20, and this one as 100 here, because we can see here that the 100 volts will be nicely split up into 50 volts, 30 volts, and 20 volts. Because that's exactly what that sentence says. So I'm going to use a voltmeter, and I show that right here we got 50 volts. Then over here we got, oops, there's the junction, 30 volts. And then over here we got 20 volts. Okay. I'm going to take the voltmeter away. What I want to say, the current being measured is going to be the same everywhere. So a moment ago we measured 1 amp, so I'm going to put the current meter in a different place, and it says 1 amps. And if I yet put it somewhere else, I have to be fast doing this here, because otherwise these junctions there connecting themselves kind of more or less automatically. It's kind of nice that they do that, but sometimes they just do it too fast. And so when I put it down here, I again have 1 amps. I'm sorry, 1 amp. So the current is flowing the same everywhere. Okay, let's go back to this one here. So what I just showed is what the book is saying, that here we have 50 volts on this resistor, 30 volts on this one, 20 volts on this one, and again individually the current is, for example, 20 ohms, 20 volts divided by 20 ohms, and that of course is 1 amp. So again, this was the individual one. Which goes to this one here. And then of course it would be also 30 volts divided by 30 ohms, 50 volts divided by 50 ohms. And a total current of 1 amp applies to all of them. Electric current has only a single pathway through the circuit. This means that the current passing through the resistance of each electrical device along the pathway is the same, in this case 1 amp. And that means that the total current is that the total power is 1 amp times 100 volts, which is 100 watts. Okay, so 100 watts is what the total power is. And you may recall from the previous problem that for just a 50 ohm resistor we actually had 200 watts. Okay, and for the light bulbs here we calculated 3 watts for 3 identical light bulbs, and these 3 identical light bulbs, they actually have to share those 3 watts, which means each of them just gets 1 watt. You can again see that by calculating 2 volts times the individual, or the total 0.5 amps. So each one of them gets 1 watt, compared to the single light bulb that gets actually 9 watts. Same light bulb, same voltage, just one light bulb gets 9 watts. Here these 3 you have to share the 3 watts right here, which means each one of them gets 1. And that's what we saw in the simulation earlier, that with the 3 light bulbs in series, they're a whole lot fainter than if you just have one of them in there. Okay, what is the total resistance? Well, again, they're going to add up as equivalent resistance equals the first resistance plus the second plus the third. So this is the really important information that may not be in the book, but that I do want you to be aware of and do calculations with it. So in this case here it's 50 ohms plus 30 plus 20, and that comes out to a total of 100 ohms. And again, if we look at Ohm's law for the total, then we would have the total current equals 100 volts divided by 100 ohms as the total resistance, and that of course comes out to 1 amps. Okay, one more little thing, and that is Kirchhoff's loop rule, which says that when we add the voltages around here, we come up with the zero voltage that we have on this side. The book says the supply voltage is equal to the sum of the individual voltage drops across each device. And so as we go up here 6 volts inside the battery, then we have voltage drops of 2 volts, 2 volts, 2 volts, which of course add up to 6 volts. Or if we go around once, it would be 6 volts up and then 2 down, 2 down, 2 down, which returns to the 0 over here. Same thing here, 100 volts of course equals 50 plus 30 plus 20, or inside the battery we go up 100 volts and then we subtract 50, 30, 20 and come back to 0 volts on the minus or ground side of the battery.